Hi, everyone. Thanks for coming to our talk. This talk is what's new in PySpark. We will introduce the new features introduced in mainly Spark 4.0. We are introducing this talk. Both of us are Databricks senior software engineers, and also Apache Spark contributor, committer, and PMC members. We will go through these topics today. Let's go from the first topic. The first topic is the table valued functions. This is, as you may know, this is available in the SQL, but these are missing in the DataFrame APIs. So, and these functions are returning the multiple rows, possibly with multiple commas, rather than a single value. In Spark, this idea already exists. Functions like explode, inline, and more recently, variant explode or something like that, which take a column and return a table. But now in PySpark, you can also write your own custom TVFs using user-defined table function or UDTF API. That's what we'll dive into next. Here's a quick example of one of the built-in table valued functions, variant explode. It takes a variant column, in this case created by parsing a JSON string, and returns a table of key value pairs. This is a TVF used as a top-level table. No joins yet, no correlation, just a function that outputs a table directly. And, just to note, TVFs are exposed through spark.tvf namespace. So you call things like spark.tvf.variantExplode, something like that, to use them from Python. Later, we'll see how to use TVFs within DataFrame pipelines using lateral joins. Before we talk about UDTFs, let's take a look at the built-in TVFs that currently Spark provides. These have been available in SQL, but now available in DataFrame API. All of these TVFs are accessible through the TVF, spark.tvf namespace, as I mentioned. So you need to call like spark.tvf, explode, blah, 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 spark.tvf, stack, blah, 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 and so on. And you can use them as standalone tables or join them with other data frames. And we'll explore both patterns soon. Okay, next topic is Python UDTF, or Python user-defined table function. This is the way to define your own TVF using Python. Unlike scalar UDFs, which returns a single value, UDFs can return multiple rows for a single input row. You implement UDF by writing a class with an eval method that yields rows using Python's generator semantics or return an iterator of values. Spark will call this method for each input row and collect all the yielded results as a table. UDFs are decorated with @UDTF decorator, which tells Spark how to register and use them. Similar to how @UDF or @PandasUDF decorators work for UDFs. Yeah, this is the simple UDF, range with square. It takes two arguments, start and end. Yeah. And yields each integer in that range, along with its square. The UDTF decorator registers the function and declares the output schema, in this case, two columns, num and squared. Internally, the eval method is just a generator. It loops through the range and yields rows one at a time. This is the clean way to express logic that needs to expand one input row into many. And this shows a simple example of using the UDTF by passing two literals, 1 and 4. The result is the data frame with 3 rows, the numbers 1 through 3 and their squares. The output structure matches what we declared with the @UDTF decorator, two columns named num and square. If the UDTF is registered, you can also use it directly in SQL. For example, select star from range with square 1 and 4. This kind of interface makes UDTFs convenient and consistent across both PySpark and SQL workflows. And in addition to that, there's a polymorphic UDTF. By default, the normal UDTF have fixed return schema as we saw in the previous example. But sometimes we want that schema to depend on the input. That's where polymorphic UDTF come in. They allow you to define dynamic output schemas which are determined at runtime. For example, the number of output columns might depend on a parameter value, or the type of the output might depend on the input type. To enable this, you define a static method called analyze inside your UDTF class. This method receives argument metadata and returns the output, returns the output schema as an analyze result object. Note that if you define analyze method, the return type previously passed to @UDTF decorator should be omitted because it will be determined later. We'll look at the example of that next. Here's the polymorphic UDTF example. This is called repeat. It takes a value and a count and emits that value multiple times. This function isn't just generic in behavior, it's also generic in output type. The key is the analyze method. It inspects the argument types and dynamically returns a schema, in this case, a single column that inherits the type of the first argument. This makes the function type flexible while still enabling schema inference and validation. Because repeat is a polymorphic UDTF, it adapts to different input types, string, integer, and so on, and carries the input, carries that type into the output. In each case of these examples, the UDTF produce the repeated values in a single column named X with the correct type automatically used. If you use integer as the value, the return type will be also integer. If it's string, the return type will be string. This is one of the most powerful use cases for polymorphic UDTF, defining a generic table behavior once and having it work many types with correct schema handling. Okay, next topic is subquery DataFrame APIs. Subqueries are now supported in the DataFrame API, not just in SQL. This enables nested logic and composable pipelines while keeping your code fully in Python. You can write both correlated and uncorrelated subqueries. The supported patterns include df.exists and not df.exist for exist or not exist subqueries. And also, similarly, if you call df.scalar, it will behave the same as the scalar subquery. That returns a single value. And also, call, this is a column object. Call.isIn and passing the df object. This is for in subqueries. This is actually supported from Spark 4.1. Yeah. And these tools are key for writing modular and expressive Python PySpark pipelines, and especially when joining with lateral logic or UDTFs. Here's an example of a correlated subquery in the DataFrame API. We are filtering customers to only those who have at least one sales record with amount greater than 100. The subquery on sales reference a column from the outer customer's query. Specifically here, a customer ID. To do that, we need to call .outer against the column on the outer column, making the correlation explicit. This is just like writing exists, blah, blah, blah in SQL, but now fully in PySpark code. Beyond exists, the DataFrame API supports a few more subquery styles, as I mentioned before. First, scalar subqueries using .scalar. This extracts a single value from a subquery, just like the SQL above. Second, you can express not exist using this tilde, not operator with .exists. Exactly how you'd invert any Boolean expressions. And third and finally, Spark 4.1, as I mentioned before, introduces in subqueries with call.isIn and it should take a DataFrame object. This lets you test membership of a value against the subquery's output. Again, very similar to SQL. These patterns let you stay fully within the DataFrame API while still writing powerful nested logic. Yeah, then lateral join. Next, the lateral join is one of the important feature of the subqueries related features. This is, lateral join allows you to join each row with the result of a function or subquery, and that can depend on that row's values. This is what makes row-wise expansion possible, such as calling UDTF that takes input columns and returns multiple output rows. In PySpark, you use the lateral join to express this. This replaces Seeker's lateral join clause and works cleanly in code. Let's look at some examples, starting with the built-in TVF. This is an example of a lateral join with a built-in TVF, variant exploit, again here. We start by passing JSON strings into variant columns using parstation JSON, like what we did previously, but this time we select it as a column. Previously, it was like from the literal value, but this time we can use the column object. Then we call the lateral join with the spark.tvf.variant_exploit, passing in the parsed column using .outer, since it comes from the left table, not in the variant exploit. This joins each input row with the exploded key value pairs of the JSON object, producing multiple rows per input. A clean row-wise expansion. Now let's see the same pattern with the Python UDTF. This is the same range with square UDTF as we saw earlier, but now applied row-wise with lateral join. For each row in the DataFrame, we invoke the UDTF with start and end as inputs, and expand it into multiple output rows. Again, .outer is needed to reference columns from the left-hand side. As you can see, the input row 1 and 4, it generates 3 rows, and for the other input, 1 and 12, it generates 2 rows and put them all together. This is how lateral joins generate to custom table logic, giving you a powerful Python native way to express expansion and nested results. Alternatively, TVFs can take table argument. Entire data frames passed into the function for row-wise processing. Although currently none of the built-in TVFs allow this, Python UDTF can take advantage of table arguments. To do this, you use the asTable method to be more precise. Oh, okay, the slide is right. df.asTable method when passing the data frame as an argument. This signals that it should be treated as a table argument. Inside the UDTF, each row from the input table is passed individually to eval as a row object, just like a structured input record. This opens up powerful use cases where your UDTF can scan, filter, reshape rows coming from another data frame, one at a time. Yeah, this UDF repeat rows takes a table argument where, where each row contains a value x and a repeat count n. Inside eval, we simply emit the value x repeated n times. This is a simple but powerful example of row-wise expansion, where a single input row results in multiple output rows. UDTFs give you the flexibility to define these behaviors in pure Python, while preserving schema and row structure. Okay, here's how we apply the repeat rows UDTF. The input data frame has columns x and n, and we call df.asTable to pass it into the UDTF. For the input 1 and 3, we get 3 rows of 10. And for 20 and 1, we get 1 row of 20. This makes it easy to implement column fan-out logic across structured rows, and something not easily done with standard DataFrame transforms alone. Summary so far, we've seen how these features work independently and now how they work together. TVFs return structured row set, either built-in or custom UDTFs. Subqueries allows nested logic that makes your pipeline modular and expressive. And lateral joins and table arguments are what tie these together, enabling row-wise application of table returning logic while supporting correlation and expansion patterns. Together, they let you build complex, composable data pipelines without leaving the DataFrame API. Okay, I'm gonna switch here with Xinrong. Please welcome her.
Yeah, thanks, Takuya, for the great introduction. I'm Xinrong, and now we are going to dive into the PySpark native plotting and UDF unified profiling. So let's talk about native plotting first. So in PySpark, data frames are built for like big data processing. They are very good at it, but we didn't have built-in plotting. So it didn't provide the visualizations. Users had to convert the data frame, the PySpark data frame, to pandas frame or pandas on Spark frame in order to do the plotting. That's not very convenient. And also, like for pandas or pandas on Spark frame, they have the index column, but the index concept does not exist in PySpark. So that adds friction. Also, you have the performance and code complexity cost. And that's why we introduced PySpark native plotting. There's no conversion, no mismatch. You just like plot directly from your PySpark data frame. And you can just call .plot on your PySpark data frame, and you can get the visualization. And it worked the same between the Spark Classic and Spark Connect, and it's backed by the Plotly library. The API matches what users already know from Pandas or Pandas on Spark. You can use method chaining style, like df.plot.line for line plots, or you can pass in the line to the canned parameter of the plot API. They both work. We support all common plot types, and here we categorize them by how much data they need. So first, it's called like top n rows. For plots like bar, horizontal bar, pie, scatter plots, we just use the first n rows. Here, n equals to like 1,000 by default, but it's configurable. It's fast and readable. It's very good for quick insights. And the second, we call it sample data. So like for line and arrow plots, for example, they use sampling. This works well for showing the trends in big data, like in large data sets without scanning everything. And the third one is called global metrics. So plots like histograms, box plots, or KDE plots, they need the full data set to be accurate. So we compute full statistics to show the distributions and outliers. And this design balances both performance and data insights across different plot types. Here we will see a very simple example. We have a very simple data frame. It shows the monthly active users for products over several months. And each row gives us the number of users for one product in 1 month. To visualize this, we use a grouped bar chart. So the x-axis shows the mass here, and the y-axis indicates the user counts. And each product will get a different color. And thanks to this bar mode parameter, bars are grouped side by side for comparison. This is the output plot. It helps us compare monthly usage across products. So for example, we can quickly see whether one product consistently leads in user count. Here is the product A. We can also use the line plot to show product growth trend. And this line chart shows how each product sales changed over time. It's useful for spotting trends and patterns month to month. So that's all for native plotting. Now let's switch gears and talk about the profiling, especially for UDF profiling. UDFs are a powerful feature in PySpark, but it's also a performance blind spot because it runs on executors like distributed computation. So it's hard to know what's taking time or using memory. So that's why we introduced PySpark UDF profiling, and it consists of performance and memory profiling. It works for all types of UDFs and derived functions, for example, map in pandas. It works consistently across Spark Classic and Spark Connect. It has a very simple set of API we will see later as well. And it supports registered UDF. So even if you wrap your UDF in a SQL statement, you can still get insight. So here's the API. Very simple, we have 3 APIs. So for show, spark.profile.show, you can view the profiling results. And to save the results, you use the dump. And to reset everything and start fresh, we can call spark.profile.clear. Now let's focus on the performance profiling. So it's great for identifying the costly logic inside your user-defined functions. It uses the Python built-in C profile, and it checks how many times each function is called in your UDF and how much time is spent. And what's powerful is it runs across all executors, so we can see the distributed behavior in a summary. And this helps identify the slow or inefficient logic in your UDF. So this example shows how easy it is to profile a UDF. Here we define a very simple pandas UDF called add1, and very intuitive, just add 1 to a number. And here we register the performance profiler using the Spark conf. And then we execute the UDF add1 using by the client. And then we call the show API we just mentioned. Here's the output of our performance profiler. So it shows that we have 1,800 function calls and the timing details. So each line includes the function name, the number of calls, and how much time was spent per call. And here, the UDF ID in the profiling output, it matches the one in the Spark plan, which can achieved by the explain API in PySpark. So you can easily trace which UDF you are profiling. So that's about performance profiling. Now let's look at memory profiling. So memory profiling, we can track how much memory each line of your UDF consumes. And this can help us see real memory usage specs, which can help detect leaks or inefficiencies. It works in a distributed context, just as the performance profiler. So we can get the overview across executors. To enable it, we need to install the memory profiler library in your cluster. And here's an example. It uses the same pandas UDF as before, like the add one. But this time, we register the memory profiler with this varconf. And we execute the UDF. Finally, we call the show API to show the memory profile. Here is the output profile. So it shows the line by line memory usage and memory increments and the occurrences. Now, let's see a few real-life scenarios where PySpark UDF profiling helps. So first, you can find hot loops in your UDF by the performance profiler. It shows which function runs the most or takes the most time. And second, the memory profiler can help you catch lines of code in your UDF that consumes a lot of memory. For example, if you are preparing data for your ML model, and there will be a lot of temporary data created. With this memory profiling tool, you can just avoid the memory specs. And third, we can compare different UDF implementations and find the best tool. This is we will dive into the comparing UDF implementations, how the profiling tool can help us achieve that. There's a very simple but common step in data pipelines that is we need to clean up the text. Let's say we have a review data frame, and it just consists of customer reviews in the string format. We often need to make the text consistent before using it. So we want to turn the text to lowercase and remove all the punctuations, keep only words. And in this way, it's just easy to count, compare, and analyze later. So the code defines a Python UDF, which is called normalized text. And it tokenizes each row and lowercase the review string. And again, we register the perf profiler using the Spark conf. And we apply to the review column and execute the UDF. We want to show the profile result. And we can clearly see that the function normalized text is actually called a million times because the original data frame has 1 million rows, and Python UDF is executed row by row. So it's intuitive that it's 1 million calls of this function. And it took 3.5 seconds as cumulative time, which include the called functions. And then we want to try how pandas UDF works. Will it achieve a better performance? So we define a pandas UDF here, which is vectorized and more efficient in general. We call it improved normalized text. It basically does the same thing, lowercase your review text string, and then tokenize it. Again, we register the perf performance profiler, and then apply to review column, execute it, and finally show the profile result. And in the vectorized pandas UDF case, data is processed in batches, like 5,000 rows per batch here, and it results in only like 200 UDF calls total for the improved normalized text. And for the cumulative time, it takes around like 2.1 seconds, even though it has the same logic. So by switching from a scalar Python UDF to a vectorized pandas UDF, we reduced the cumulative runtime for the UDF from 3.5 seconds to 2.1 seconds. And this example runs only on 1 million rows. But as data scales, the performance gap widens. And in this case, a pandas UDF is strongly preferred. So to summarize, with native plotting, PySpark becomes more intuitive and accessible by providing you a set of plotting API that can apply directly to DataFrame. And with the unified UDF profiling, you can gain deep visibility into performance memory and helping you write more efficient and linear PySpark code. That's all I wanted to share today. And now let's welcome back Takuya to take us through like what's new in PySpark. Thank you.
Thank you, Xinrong. Let's wrap up with a few highlights of what's available and what's in progress. First, Spark 4.0 introduced the Python data source API as well, which allows you to define Spark data source entirely in Python. No JVM code required to run this data source. This opens the door to simpler connectors and testing tools and lightweight adapters. Actually, I saw there are some sessions during this DICE and about the Python data source. So you may want to also join them. The second one is arrow UDFs. This is under actively development. This will be a first modern replacement for pandas UDFs, operating directly on arrow object, arrow batches, without conversion to pandas. They are fully vectorized and promise both speed and simplicity. But they are still work in progress. But I guess it will be available in Spark 4.1. Thank you. That's all from our talk.